first problem is about partial fraction decomposition. We are given a rational function here, and we are asked to write down the setup for a partial fraction decomposition. So we need to look at the denominators. Every factor of the denominator will give us summands, and we will get several summands if they occur to a power. So what we get is some x minus 1 single, because it occurs to power 1. We get x plus 5, and this occurs to power 2, so we also get something with x plus 5 squared. We get x squared plus 1, and again, because it occurs to power 2, we get it twice, and we get a term for x squared plus 2, and we get this once. Now for the numerators, if our denominator comes from a term of degree 1, the numerator will be just a variable, so we get a, b, c here. If we have a quadratic term in the denominator, we get a linear term in the numerator, so here we get dx plus e, fx plus g, and hx plus I, and that is the setup. The problem asks explicitly we do not need to solve for, so that would be very tedious work, but the problem is done already at this point. Problem 3 is about improper integrals. We are asked to determine whether these integrals converge or diverge. First we have 1 over x cubed plus 1, integral from 1 to infinity. Finding an antiderivative for this is hard, so we probably need to do comparison. Can we compare 1 over x cubed plus 1 with something we know? Well, 1 over x cubed plus 1 looks very similar to 1 over x cubed. What can we tell about these? Well, x cubed plus 1 is greater or equal than x cubed. So 1 over x cubed plus 1 is always smaller or equal to 1 over x cubed. We know already from the lecture that the integral over 1 over x cubed converges, because this is an integral for a power of p. So we can use the comparison test, and we know that the integral over 1 over x cubed plus 1 dx from 1 to infinity also converges. In part b, we have the integral over 2 plus sine x over x. What does this look similar to? Well, we have 2 plus sine x is somewhere bobbling between 1 and 3, so this is something almost constant, so we could compare it with, say, 1 over x. We know that 2 plus sine x is always greater or equal to 1, so this is greater or equal than 1 over x. We know that the integral from 1 to infinity over 1 over x diverges. Therefore, by comparison test, we have that the integral from 1 to infinity over 2 plus sine x over x also diverges. Problem 4 is about limits. It's about proving the limit for a particular sequence. As a help, first we are asking you to repeat the definition. The sequence converges to a number L if for every positive epsilon we have an integer big N, such that for all little n greater or equal than big N, we have that an is at most epsilon away from big L. If you choose smaller or equal or strictly larger here, that is also fine. These basically would give you equivalent definitions. Now we want to do this for a particular sequence, and part B is basically an auxiliary part which helps you on the way to it, namely what we typically need to do for a given epsilon. We need to calculate the big N value so that things hold. So let's look at the absolute value of an minus L. In our case L is 1. This is equal to n to the 4 plus 1 divided by n to the 4 minus 1. We can bring this on a common denominator and we get n to the 4 plus 1 minus n to the 4 divided by n to the 4, which is just 1 divided by n to the 4, which, because n is always positive, is the same as 1 over n to the 4. And now we demand that this should be smaller than epsilon. So if this is smaller than epsilon, we divide. We want to solve this for little n. So we divide by epsilon. Epsilon is greater than 0. We multiply with n to the 4. So we get that n to the 4 must be greater than 1 over epsilon, and therefore n must be greater than the fourth root of 1 over epsilon, and that is what we set as our big N. So we have this value for big N, and with this we now can write the actual proof for convergence. Here the text is very important because that is really connecting the expressions which we have. So we assume that we are given epsilon greater than 0. Now we need to show the definition. We need to show that for every epsilon we have such an n with such the condition holds. So we start, we are given some epsilon, we let big N, and here we just copy what we calculated in our auxiliary calculation, the fourth root of 1 over epsilon. Then for any little n which is greater than big N, we get that an minus 1, the 1 here, because we have limit 1, we claim limit 1, this is equal to, okay, now we basically duplicate the calculation from above. This is n to the 4 plus 1 divided by n to the 4 minus 1, which by the same argument as above is 1 over n to the 4, which is 1 over n to the 4. Okay, now we're using that little n is bigger than big N, so 1 over n to the 4 is smaller than 1 over big N to the 4. And what was big N? Big N is the fourth root of 1 over epsilon to the 4, and this we can simplify as 1 over epsilon, which is epsilon. That proves the theorem, because now we have shown that for any epsilon greater 0 we can choose n in a suitable way, and then we can show that for if little n is bigger than big N, we have that an minus 1 is smaller than epsilon, and that's what we had to show.